Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome my own PhD student, ATUL GOTHE from IMPAN at the University of Warsaw, who is currently residing in Canada. He will tell us everything and more about a quantum CW complex structure for quantum real projective spaces. ATUL, it's all yours. Take it away.
Yeah. Thank you for the kind introduction. Yeah, so as the title suggests, I'll talk a bit about the quantum CW complex structure for quantum real projective spaces. I'll come to what each of those things mean. So I'll just refresh what do we mean by CW complex classically. So if we have an X to be a topological space, then a CW decomposition of X is some sequence of subspaces x0, x1, xn, such that when the first space x0, it is a discrete space. Xn is obtained from xn minus 1 by attaching over some n balls along the boundary, along the attaching maps, spheres to xn minus 1. And X is homeomorphic to the union over xn with the weak topology. So that just classically, a simple example would be if we glue two hemispheres along the boundary equator, we just get a sphere. So we just attach two balls here along the common equator to get a sphere like this. So that's a classical example of a classical CW complex. Usually CW complexes are nice category of not nice collection of spaces which people usually study so that they have nice properties, they have nice K-theoretic computations and stuff. So how do we quantize this? A way to quantize this is uh, in some way some categorical way of doing this. So to get to quantum CW complex, there are a few definitions which are in line. So first of all, you start with an unpointed Waldhausen category. So an unpointed Waldhausen category C is a category which has an initial object phi, uh, terminal object star, such that we have two classes of morphisms. First, which are called cofibrations, which are denoted by inclusions, and we have weak equivalences, which are denoted by arrow with a tilde on top, such that a few conditions are needed to be satisfied. So first of all isomorphisms in this category are in fact cofibrations, and composition is closed, and cofibrations are closed under composition. That is, if we compose to cofibration, the composition is again a cofibration. And for any object x, the unique morphism from the initial object phi to x, this is in fact a cofibration as well. And if x to y is a cofibration, then and we have any morphism x to x tilde, then if we construct the push out, if it exists, then x tilde to this push out, this is also a cofibration. So these are the conditions for existence, or not conditions for cofibrations. And for weak equivalences, we have the conditions that all isomorphisms are again weak equivalences as well. The composition of weak equivalence is again a weak equivalence as expected. And the third condition, which is a bit more complicated, that if we have a commutative diagram of this form, where we have we have weak equivalence from, or sorry, a cofibration from x to y, x tilde to y tilde, and we have cofibrations in the vertical direction, then the induced map Z, like the induced map on the pushouts, is also a weak equivalence. So if we push out Z and Y over this big one over the common space X, and if we push out Z and Y tilde over the common space X tilde, then we also get a weak equivalence on the pushouts. So these six conditions, these are the defining conditions for an unpointed Waldhausen category. An example of such a category would be the homotopy category of topological spaces. And to this unpointed Waldhausen category, we have to have some sort of weak equivalence or a weakening of this category, which is called a CW Waldhausen category, or co-fibration weakening Waldhausen, which means that if we have any push out of the form that y goes to y tilde and y goes to z tilde, and a push out is onto z double tilde, then if h tilde is a weak equivalence, this one, then it also means that g is a weak equivalence as well, and it's an if and only if condition. So if this further condition is satisfied for an unpointed Waldhausen category, we call it to be a CW Waldhausen category. So
Sorry,
why
may I
do
have a
we?
question?
Yeah, sure.
You mentioned that this homotopy category is an example of a Waldhausen category. So, what are the weak equivalences?
Weak equivalences would be continuous functions which induce, I think, isomorphisms on, not isomorphisms, but continuous functions which are homotopy equivalences.
So, what is the distinction in this
Isomorphism
specific?
of homotopy groups. There are weak equivalences in the sense of algebraic topology.
So isomorphism is a homotopy equivalence, and weak equivalence is a weak homotopy equivalence. Yes, is it right?
Yes. It
Okay.
introduces isomorphism, but
Yeah.
on homotopy groups.
Homotopy, yeah.
Okay, thank you.
So why do we need all this structure for CW Waldhausen category? So if we want to go from classical to non-commutative, as we go from commutative using Gelf and Naimark, we want to think of the opposite category of unital C-star algebras, because if we look at opposite category of commutative C-star algebras by Gelf and Naimark, we know that they are opposite of, the dual of commutative C-star algebras are locally compact Hausdorff spaces, or unital C-star algebras are compact Hausdorff spaces. So we want to look at the opposite category of unital C-star algebras. So if we consider the opposite category of unital C-star algebras such that the unital star homomorphisms as the opposite morphisms, the zero C-star algebra as the initial object, the space of complex numbers to be the terminal object, surjective unital star homomorphisms is cofibrations, and unital star homomorphisms which induce an isomorphism on K theory as equivalence. This particular category is in fact a CW Waldhausen category. And once we have such, this is why kind of we need this, because once we have the CW Waldhausen category of this unital C star algebras, we can think of constructing some sort of quantum CW complexes in which we want to, these non-commutative spaces are just formal duals of C star algebras, and the pushouts in this opposite category will correspond to pullbacks in the category of C star algebra. So to define this quantum CW complex, so a finite quantum CW complex is an object such that we have a sequence of cofibrations in xd0, xd1, xt, and so on and so forth. Of course, because here the morphisms are in this direction, but on the C star algebra level, everything goes in the opposite direction. So on the C star algebra level, the morphisms are in the opposite directions, such that the first element xd0, it's finite, and we can go to the higher xdk from xdk minus 1 by pushing out over some non-commutative balls over the boundary non-commutative spheres.
What does it mean to be finite in this setting?
For the C-star algebras are finite dimensional, so that they correspond to discrete finite spaces in a topological sense. And here, these non-commutative balls, as C-star algebras, they can have multiple ways. For instance, for three-dimensional balls, non-commutative balls, we can have C of BQ3, which I'll come to what this means. But we also can have something like, say, the Toeplitz tensor product with C minus 1, 1. And we have an inclusion this way. So these are two different kinds of non-commutative balls. They do have a K equivalence between them. That is a star homomorphism which induces an isomorphism on the K theory. But we can see that in the non-commutative case, we can have different kinds of C-star algebras for non-commutative balls and spheres. And classically, of course, they do mean the same thing because B3 is homeomorphic to the cylinder with the top and bottom attached to it, which is kind of this. And this is the 3 ball, but yeah. Any questions so far? Okay. So moving on. So once we have these quantum CW complexes, we want to have some these morphisms which induce equal or isomorphisms on K theory or so on and so forth. We need some examples of C-star algebras which are usually nice and well behaving, so that at least in some ways we can have certain nice star homomorphisms and at least have a way to construct these pullbacks. So here, of course, when we say these are pushouts in the opposite category, we want to construct pullbacks in the category of C-star algebras. So we kind of want some nice C-star algebras. And one way to define such nice C-star algebras is through topological graph. So a topological graph, it's, as the name suggests, it's a generalization of a usual directed graph. So a usual directed graph is, for instance, we have two vertices, we have say an edge here and an edge here. So this is just a classical usual directed graph. So we have two vertices and we have two edges here. So what is a topological graph? It generalizes this notion of a directed graph such that we have a quadruple, we have E0, E1, the source map, the range map, such that E0 and E1 are locally compact spaces. And here by locally compact, I mean that they are locally compact Hausdorff. Everything will, all the topological spaces which we'll consider will be Hausdorff. So locally compact means locally compact and Hausdorff spaces, such that the source and range maps are of course continuous, but we further require that this range map, this is a local homeomorphism. So once we have such a topological graph, like an example of such would be if we have E0 and E1 to have some discrete topology. Say for instance like this, if E0 and E1 are discrete, then we have just the usual directed graph. And say for instance, we have a topological dynamical system, which is X comma sigma. That is, X is a locally compact space and sigma is a homeomorphism of X. Then if we define our topological graph to be E0 and E1 both to be the same space X, S to be the homeomorphism sigma, while range to be the identity map. This is another example of a topological graph, which of course does not have a discrete topology. So once we have a topological graph, we can construct a C-star correspondence for this. So the C-star correspondence is, we consider the C0, E0 functions, the functions which vanish at infinity for E0 on E0, a space Xe, which shall come to what it means, and an inner product on this module. So the Hilbert module structure here, the inner product is such that any function xi and eta, the inner product is defined by, we take xi of E bar and eta of E and take the sum over the pre-image of the range. Oh, sorry. So we take the pre-image over the range of the vertex V. Because R, we have defined R to be a local homeomorphism, it means that when we take the pre-image of a discrete subset, which is just V, the pre-image is also discrete. So taking the sum here makes total sense. So we take the inner product xi of xi and eta to be xi of E bar, eta phi. And we define this space Xe to be such that all such functions CB, all the functions xi in the bounded continuous functions on E1, such that when we take the inner product of xi with itself, it ends up in C0 of E0. So it's a subspace of all CB of E1. And we define the module multiplication on the right by taking precomposition with range, that is psi into f of E acts as psi of E for f of range of E, and the left multiplication f psi of E, this gives f of S of E psi of E. So here we have a Hilbert bimodule structure. We have a something with an inner product which takes the values in C0 of E0, and we do have a left and right multiplication. And to complete this Hilbert bimodule into left action, we take the left action is just precomposition with source again. So we can define pi s from C0 of E0 to the bounded operators on this module by taking pi s of f on xi. It acts by taking the pre-image with source.
Sorry, so I'm a little bit confused. What is the difference between this left action defined in the third line from the bottom and also the last line?
Yeah, so this is the module multiplication and this is the left action. Of course, they are the same thing. They are defined in the same way, but in some ways they are kind of different because this is a multiplication, but while this is an action.
You act by multiplication.
Yeah, we act, yeah.
Okay, so you view it like an operator on this Hilbert module, yes?
Yeah.
Okay.
Yeah, so of course the examples are if E0 and E1 are discrete, then we just get the usual directed graphs. And for our topological dynamical system, we also have a topological graph for this dynamical system. So now, why do we need topology and stuff? Or what kind of subsets do we care about? So first of all, we want to define the sinks. So E0 of sinks or the sink vertices which are sinks are E0, but without the vertices which are in the image of the source of closure. So here, because of topology, we need the closure here, and sinks so will be an open set. And E0 of n are all the vertices in E0 such that there exists at least one neighborhood of V, such that the pre-image of this V under the source map is compact. So these are called the fin is for finite vertices because pre-image of some neighborhood is compact. And E0 regular are all the finite vertices which are not in the closure of the sinks, and all the singular vertices are all just regular vertices. So if we have just the usual discrete topology on E0 and E1, then taking the closure here does not matter. So everything agrees with just the discrete directed case. But when we have non-discrete topology, we can have something more interesting going on. So for instance, if let E0, E1 be R with the usual topology, say the range map is identity, while the source map is taking the mod. So for this, we can have that the image of the source, and if we take the closure, it is just 0 to infinity. So the closure of sinks becomes so because E0 sink is E0 without S of even closure. So E0 sinks are just minus infinity to 0. So the closure becomes 0 included. Similarly, the regular vertices are all the positive non-zero numbers, and all the singular vertices are all the non-positive numbers, which are minus infinity to 0. So here we can see that because of taking the closures and all of this, 0 becomes a singular vertex, even though it's not a sink or an infinite emitter. So for a classical directed graph, there are two types of singular vertices, which are either sinks.
Wait, I have a question. So when you say infinite emitter in this context, you mean that the pre-image of the source map is not compact, right?
Yeah.
Okay.
So it's not a finite vertex.
Okay.
So here 0 is a sink even. So we kind of have new kinds of singular vertices which come up. For usual examples, usually they won't be a problem, but we can see that they can and do exist, that some new kinds of singular vertices. And so the C-star algebra of this topological graph is just the Kunz-Pimsner algebra of the C-star correspondence, which we have defined here, which is just the correspondence C0 of E0, XC, and this. So taking the Kunz-Pimsner algebra of this correspondence, that gives us the C-star algebra for this topological graph. So if E0 and E1 are discrete, then as expected, the C-star of E is just the usual C-star algebra of a directed graph. Say now for the homeomorphism, say we'll look at the other example. If x comma sigma is a topological dynamical system, that is, say X is a locally compact Hausdorff space, sigma is a homeomorphism. Then again with the same topological graph, E0, E1 to be X, source to be the sigma, and range to be the identity. We have that the C-star algebra corresponding to this is the usual cross product C-star algebra or homeomorphism C-star algebra of this dynamical system. So these topological graphs are a way to generalize usual directed graphs while also generalizing homeomorphism C-star algebras. There are more examples of topological graphs which are not either of them. They are not the C-star algebra of a discrete directed graph or a homeomorphism C-star algebra. There are examples of such, and we'll come to that. But like the original motivation for defining these topological graphs was kind of to generalize both these notions at once. So now that we have topological graphs, we want to look at ways how do we connect two different topological graphs. So to define such connection between two topological graphs, we define something called a factor map. So a factor map M, so a factor map M, say this, it's a pair of maps. So because a graph is composed of two, E0 and E1, it's expected that we will need two maps, M0 and M1, so which are proper maps. So proper maps mean that pre-image of compact sets are compact. So I'll just write it down just in case. So M0 and M1 are proper. So if E0 and E1 are discrete, then proper maps just mean finite to one. But for non-discrete, we can have more examples of proper maps, such that two conditions are satisfied. So M0 goes to vertices, M1 goes to edges, such that two conditions are satisfied. First of all, they have to uh, behave well with the range and the source map. That is, if we take the image of an edge under M1 first and then take the range, it should be the same as if taking the range first and then taking M0. And the same with the source. That if we take the image first and the source, it should be the same as taking the source first and then the image. Here, maybe just for clarification, I can add that this is range in E while this is range in F. And the same with here.
I have
So
a
they
question.
should, yeah.
What is the motivation for the name, a factor map?
I think there are factor maps which are they come from dynamical systems. There is some notion of factor maps and dynamical systems, which are kind of related to this. I don't remember what the exact definition was, but I think the terminology comes from uh, the theory of dynamical systems. Is it okay?
Okay, thank you.
Yeah. So now if E and the second condition, which is also called target bijectivity. So what this means is if we have an edge E prime in the codomain, and a vertex V in F0 in the domain of the vertices, such that the range of E prime is the image of some vertex M0V, then there exists a unique E in F1 such that M1 of E is E prime and range of E is V. So diagrammatically, it means that if we have an so if we have an edge here, if we have an edge here in E prime such that there's a vertex or and a vertex V here, which maps to the range of this, then there exists a unique E here such that this also maps to E prime. That's kind of target bijectivity.
ATUL, and how about phrasing it in the form of a fallback of target map? We can do it in the discrete case, and I'm sure we can do it here.
Yeah, so we can do it such that if we have this map,
Out of places. Okay.
if we have F1 E1 via M1, so we have range to F0. Then if we have this diagram, then the map which is induced on the pullback from E0 to E1 over E0 over F1, then this is a homeomorphism.
Wait,
So-
I'm confused.
What?
Why E0? F1 should be homeomorphic with this.
Oh, sorry. Yeah. Sorry. Not on the push out, but on the pullbacks. Yeah.
And then you have F0 and F1, yes.
Yeah.
But my point is that this is can you say that this is a pullback in some topological category? Because these are very tricky things. I mean,
Yeah.
to have really a pullback in the category. In the discrete case, it's very, very easy because it's just a pullback in the category of sets and maps, period. But here you have continuous maps, but okay,
Here-
is it a pullback in the category of, I don't know, topological spaces and continuous maps?
Yeah, because M0 is proper. So
Okay.
one of the maps in this commutative diagram is a proper map. So we can have pullbacks which will exist if at least one of them, and it will be closed. So it will be a pullback just because M0 or M1, one of them is a proper map.
And that's good. And I emphasize it because this is a very important feature. Very recently, with a bunch of coworkers, we classified all possible graph homomorphisms, and I'm sure it's possible also for topological graph homomorphisms of Katsura. And the reason why we can do it so easily is precisely because of this target bijectivity condition.
Yeah.
Which basically tells you give me a vertex map, and then I can give you everything else. The only other parameter to establish is really the source map on the new graph. And that's it. Every graph homomorphism has to be of that form. Somehow, the target projectivity enforces on your domain graph to be the pullback, period. You have no other choice.
Yeah.
Okay, good. Thank you.
And once we have this factor map, then we can have a star homomorph, which will come, but A factor map, it will be called regular if all the singular vertices map into singular vertices. So maybe, yeah, regular vertices can still go to singular, but singular have to still stay inside singular vertices. So
Is it equivalent to saying that the preimage of regular is regular?
regular, yeah, it is equivalent.
Okay. Yeah, because this is by the definition, sorry.
Yeah.
It's obvious. Yeah.
So once we have such factor map, say again M is a factor map between F to E, then we have a contravariant functor such that is we have a star homomorphism in the opposite direction mu from the C star algebra corresponding to the topological graph E to F. And here these are defined using the representation of this Kunz-Pemsner algebras. Like so mu0 and mu1 are because again xe and xf are some function, so we can pre-compose xe and f1 with m0 m1 so on and so forth. So if we define this mu0 map from in the opposite direction from c0 of e0 and c0 of f0 such that f maps to f compose m0, and on mu1 it is such that xi goes to xi compose with m1, then this is in fact then there exists a unique star homomorphism which is in the opposite direction from, because the contravariance comes here. So the contravariance is in fact because of this contravariance, or and going from this to the C star algebras, this is covariance, while this is contravariant in some ways. And here TE and TF are the representations of the C star correspondence inside the Kunz-Pemsner algebra. So once we have such regular factor maps, we can then start talking about star homomorphisms between the C star algebras themselves. Any questions so far? Okay. So some more interesting things about topological graphs. So first of all, in directed graph, for instance, we have a complete classification of gauge invariant ideals of the C star algebra, which comes from just combinatorial properties of the graph. So something called heredity and saturated subsets. So to do this for topological graphs as well, we define something called an admissible pairs. So a subset x0 inside the vertices E0, it is called positively invariant, such that if there exists some edge such that it ends up in x0, then it implies that it should have started in x0 as well. So if there's an edge such that if this is in x0, then it means that this should also belong to x0. And negatively invariant, so this is something which is related to the hereditary subsets. While for the saturatedness, if we have any vertex which is in x0 and it's a regular vertex in the bigger topological graph E0, then there should exist at least one edge E such that it starts at V and ends up in x0. So it's called negatively invariant. And here, of course, it's kind of in the opposite direction, that source of E is V and range of E in x0, but here it positively invariance is in the other way. And we call the subset x0 to be invariant if it is both positively and negatively invariant. So these admissible pairs are kind of the if they are the opposite of heredity and saturated subsets, they are complements of them. And in some ways they are exactly for directed graphs, they are the complements of heredity and saturated subsets. if you are aware what those means and what they are. But here, this definition is sufficient. So if we have a pair rho x comma 0 such that both are closed subsets, so they have to be closed here. So in this definition, we don't really use topology anywhere. This is just a combinatorial description or a set theoretic description. But here we need the topology that x0 and xz are closed subsets of E0. And we call this to be an admissible pair if x0 is an invariant and the singular vertices of x0, which is defined as we take the vertices to be x0, but the edges to be, so this is the edges such that we take the pre-image of under the range of x0, such that z is in between x0 singular and E0 singular intersected with x0. So usually for many cases, x0 singular is strictly inside E0 singular intersection with x0. So z can end up in between both of them. And now, so why do we need this? So for an ideal I of the C star algebra E, we can define two sets such that these two are indeed an admissible pair. So the exact definition does not matter for now, but the idea is if we start with an ideal of the topological graph algebra, for that ideal, we can define something which is a admissible pair. And of course, there is some contravariance here as well. If we take two ideals, I1 and I2, then the admissible pair corresponding to the intersection is union of the admissible pairs themselves. So the smaller the ideal kind of becomes, the bigger the admissible pair in some ways.
Sorry, the first point, the ideal I is arbitrary.
Yeah, it need not be gauge invariant. It is just a closed ideal. And similarly, if we start with an admissible pair, we can define an ideal corresponding to this, which is I rho. So again, here, whatever the definition being there, technical definitions, but the take-home message are, yeah, the meat and potatoes is for an admissible pair, we can define a closed ideal I rho of the C star algebra itself. And the next result, which kind of is expected, that if we start with an ideal I, and we can end up in a admissible pair corresponding to it, or we can start with a admissible pair and end up in the ideal. This is a bijective correspondence between all gauge invariant ideals of OE of the C star algebra and all the admissible pairs of E. So there is some nice correspondence between the combinatorial and topological properties of the graph to the algebraic properties of the C star algebras, which is generated by the topological graph. Which again, this is just a generalization of for classical graph heredity and saturated and gauge invariant ideals. So this is just a generalization of what is already known in the literature for usual directed graphs. And if we have, and for some certain topological graphs which are called row finite, we don't even need this subset Z. We only care about x0. That is, x0 singular becomes exactly equal to E0 singular intersection with x0. So
But for arbitrary admissible pairs,
yeah.
Is there an analog of this theorem in color?
Yeah, so here I think there's something called breaking vertices as well. But here, for a row finite one, we don't have these breaking vertices. So this Z, what this Z corresponds to, if we are familiar with classical directed graph C star algebra, that Z corresponds to breaking vertices in that case, while these X0 that corresponds to hereditary and saturated subsets. And here for non-row finite, we know that heredity and saturated and breaking vertices, these correspond to gauge invariant ideals. But for row finite, we only need heredity and saturated and just gauge invariant ideals. Does that answer your question?
Yeah. So in this theorem of Katsura,
Yeah.
on one side you have these all admissible pairs.
Yeah.
Okay. But what is on the side of ideals? Is it the same construction which was written before?
Yeah,
In
this
terms of
I
these
row.
compact operators?
Yes. So any gauge invariant ideal, it comes from an admissible pair. So
Like in the discrete case.
for discrete case, the gauge invariant ideal come from some heredity and saturated subset of
Yeah.
E0.
Yeah.
Is that it, or does that answer it? Your question?
Yeah. Yeah.
Yeah. So now, why do we need this ideal structure? When we'll go and consider pullbacks, one of the important things in the pullback is the kernel of star homomorphisms. To establish how, and kernel of a gauge invariant star homomorphism is a gauge invariant ideal. So that's why kind of the ideal structure is not necessary but very useful, because if we have some way of dealing with gauge invariant ideals in terms of some subsets of the vertices, then we can talk about kernels of star homomorphisms. That is, say G is a regular closed subgraph. What this just means is G0 behaves well inside E0 and E1.
I
Some
think there's
well
a
behaving.
question. Ali, just show yourself and ask a question. But switch the
Yes.
camera on if you can.
Yes, unfortunately my camera doesn't work, but I
Okay.
have a question about your previous slide. You said that there is a correspondence between the set of gauge invariant ideal and also invariant sets is invariant subsets of the vertex. My question is that is there any nice interpretation for a gauge invariant ideal which is also an essential ideal? By an essential ideal, I mean that an ideal which intersects all other ideal non-trivially. So, is there a nice interpretation for a gauge invariant ideal which is also an essential ideal? Can one find a nice interpretation in the vertex set?
Because we have row I1 intersection is just the union of admissible pairs. So if we have an ideal I which has non-trivial intersections with any other gauge invariant ideal, maybe it can be thought of as some subset of E0 which contains all admissible pairs.
Which contains all admissible pairs?
Yeah.
Uh-huh. Uh-huh.
Because we have some sort of contravariance between intersection of ideals and unions of admissible pairs.
Mhm, mhm. Yes, I see. Okay, thank you.
So now, if G is a regular closed subgraph, again, here the exact definition does not matter, but what this means is in holistically, it means that G0 behaves well inside E0, G1 behaves well inside E1, such that when we look at the induced star homomorphism between the C star algebras, which is induced by this inclusion, then this kernel of this star homomorphism is in fact just I rho, which is defined earlier, for the admissible pair which corresponds to G0 and G0 singular. So if G embeds inside E, then when we have C star of E to C star of, since this is injective, this will be surjective. And the kernel of this map, it is in fact just, it corresponds to just G0 inside E0 and G0 singular inside E0. And both will be closed. Is it okay? Any questions so far? Okay. So now coming on to some nice examples. So first of all, what are example, or we want to get into what quantum real projective spaces are. To get there, first we need some quantum spheres. So the odd dimensional Waxman-Seibelman sphere, this is defined as the universal C star algebra, which is generated by n elements Z1, Z2, Zn, such that they commute with Q commute with each other. That is Zj, Zi is Q, Zi, Zj. Zj star Zi is Q, Zi, Zj star. And Zi star Zi is just Zi star plus 1 minus Q square. And with taking the sum of Zj, Zj star over J greater than I. And the sum over Zi, Zi star is just 1. So this is the C star algebra, which corresponds to a Q deformed sphere. And the C star algebra, which corresponds to the real projective space, as with classically, we want to look at some fixed point subalgebra of this C of SQ2n minus 1. So fixed point subalgebra specifically under the antipodal action Z2. So as RP2, for instance, so we have S2 to RP. So we have something S3 to RP3, right? Because we at this map is defined by identifying the antipodal point. So on the C star algebra level, when we define the C star algebra corresponding to a quantum real projective space, we want something which embeds RP3 inside C of S3, some quantum. So to define this, we define C of RPQ2n minus 1 as the fixed point subalgebra of C of SQ2n under the antipodal action which identifies Zj with minus Zj. And these are dimensional spheres and projective spaces. A big advantage of them is that they are in fact graph C star algebras.
Sorry,
So C of,
I'm not sure if you mentioned it, but it's definitely worth mentioning here that if you divide by the action of U1, I mean, you take U1 fixed point subalgebra, then you have complex projective spaces.
complex projective spaces, yeah.
Because it's somehow more obvious to do it, right? Because here only odd spheres are given, and if you are defining complex projective spaces, odd spheres are all that you need. And it's absolutely clear from the Waxman-Seibelman relations that they are invariant under the obvious rephasing action of U1.
Yeah.
Okay? And this is how you define complex stuff.
Yeah.
And this is very ancient. It has a very, very long history. But doing it for real, okay, ATUL will explain to you that you also have to take care of more difficult even cases, right? But in the odd cases, you can take the good old-fashioned Waxman-Seibelman spheres and restrict the U1 action to Z2 action, and voila, here you go.
Yeah. So just to write down what you just said, this is just like here, with this is just C of SQ n minus 1 with U1. The fixed points of algebra under U1 action. Or maybe 2n plus 1. Yeah, but yeah. So nice presentation of these spheres and real projective spaces are that they are in fact directed graph C-star algebras, which in particular also mean that they are topological graph C-star algebras. And C of SQ2n minus 1 is easy enough to explain. So we have just n vertices such that there's just one edge which goes from I to j such that I is less than j. So we only have edges in one way, and there is only one edge which connects Vi to Vj, and Vj is greater than I. But for RP Q2n minus 1, it's slightly more complicated. There are way more number of edges. The number of vertices remain the same, V1, V2, Vn. But for the number of vertices which connect Z, J, or I to J, number of edges here connecting Vi to Vj, I less than J. So again, everything goes in just one direction. We don't have any edges in the opposite direction. The number of these is just J minus I plus 1. So so to V1, there's just a single edge because 1 minus 1 plus 1. But for V2, we have V1 to V2, we have 2. And from V1 to V3, we have 3. And V1 to V4, we have 4, and so on and so forth. So it matters on J minus I plus 1, the number of edges which connect them. And of course, at the end, we have a loop at Vn as well.
A question, Atul.
Yeah.
I know that for the spheres, we have isomorphism of U1 sister algebra. So not only the Waxman-Soibelman is isomorphic as a sister algebra to this graph sister algebra, but also this diagonal action that defines quantum CPMs goes to the gauge action or the reverse of the gauge action. How about this RP, these real projective spaces? Is it also an isomorphism in the sense of U1 sister algebras, or do you have that there's no longer any relevance? And anyway, I'm not sure what would be U1 action on the real projective space, but it should be there somehow. No. But I mean, imagine if they take this fixed point Z2 fixed point sisters of algebra. Would it still have a natural U1 action? Possibly, yes, why not?
I don't think so, because RP3, for instance, has 5 generators, and they have whole slew of like the relations between them. There are like 25 relations or
So let me rephrase
something.
my question.
Yeah.
Take the graph sister algebra of figure 2. It surely has a gauge action. What this gauge action becomes in terms of Waxman-Soibelman generator?
That gauge action, so the U1 gauge action on the graph algebra or the U1 gauge action on the
Well,
Waxman-Soibelman?
you have a graph sister algebra. It has a canonically given gauge action. Okay.
Yeah.
Now you have an isomorphism of sister algebras. So the Z2 fixed point sister subalgebra of Waxman-Soibelman sister algebra of a quantum sphere is an image of the isomorphism. So we can transport by this isomorphism the gauge action from one sister algebra to another. And I'm just curious what this will become in terms of Waxman-Soibelman generator.
I think it's very complicated. So
It could be, yes.
yeah, because at least for real projective spaces, this mapping it looks simple enough that Zj goes to minus Zj. But in terms of the graph generators, this action corresponds to, I think, SE going to something complicated here. It's no longer just lambda SE. It becomes something more.
Yeah.
So it corresponds to some gamma
so
minus
it's very
1.
complicated. Okay.
Okay, yeah.
So this means that this antipodal action on the sphere is not visible from this
Graph point.
graph point.
No. Yeah, I mean, it is visible, but it's not simple enough.
It's
It's
not
not
simple.
just Z2 minus Z.
Okay.
Yeah.
Because for even quantum spheres and for even quantum real projective spaces, it is very easily visible with Z2 action. However, this is not a restriction of a gauge action.
Yeah.
Yeah, that's a funny thing. But here, this Z2 action is, that's I'm a bit surprised because on Watzmann-Soibelmann, right? I mean,
Yeah.
the diagonal action restricts to the antipodal action, right? Because you are rephasing your generators, and in particular, you can take your angle to be pi, and then this is multiplication by minus one.
Multiplication by minus one is the unidirection.
Exactly. So the antipodal action on the quantum spheres is exactly a restriction of a gauge action.
Yeah, it sits diagonally.
Yeah. So you are saying that here the restriction of a gauge action is complicated.
Yeah, I think so.
Okay.
Like, I'm not sure the complication, whether it happens for even case or the odd case, but in one of the cases, the antipodal action is no longer simple enough that SE just goes to minus SE on the graph generators.
Okay. Because I repeat, for quantum even spheres,
Yeah.
the antipodal action is easy to see because you have like two sinks, and we are basically
Oh.
exchanging the sinks and edges that end with sinks.
Yeah.
So it's very easy to see. However, it is by no means, there's nothing to do with the gauge action. Okay, good. I'm happy.
So once we have this even case, we can define the C-star algebras for the odd ones, which is just we take C of SQ2n and we quotient out the ideal, which is generated by the elements of the form Zn minus Zn star. So J2n plus 1, this is the ideal generated by Zn minus Zn star. So we just quotient it out, and that's what the C-star algebra of the even dimensional spheres are. And just like that, and just like the previous odd real projective spaces, the even real projective spaces are also defined by Zj plus J2n plus 1, because C of SQ2n plus 2n is defined as C of SQ2n plus 1 over this ideal. So we just want to look everything modulo this ideal J. So again, Zj just goes to minus Zj, and we take the fixed point subalgebra under this antipodal action, and the C-star algebra is called the even dimensional real projective spaces. So these even dimensional ones, these are also nice that they are also graph C-star algebras. So for RPQ2n, it's almost the same as 2n plus 1, but instead we don't have a loop here. So in 2n plus 1, for instance, for 2n plus 1, then we just have an additional edge, and we would have a loop at the end as well, like here. But for 2n, the number of vertices remain the same, all the edges remain the same here, but we don't have a loop at the end, so that the final vertex becomes a sink.
Yeah.
And C of SQ2n, it's more complicated. It's no longer which is just defined in this way, but we have now two sinks for C of SQN. We have n number of vertices, each has a loop. Again, this part remains the same, that everything we just have a single edge which goes to the next edge which is next to it or along the line. But we have two more sinks, W1 and W2, such that each of the vertex also emit to these two sinks, W1 and W2. So this is the presentation for the graph C-star algebra, or this is isomorphic to the C-star
Could
algebra
you
of
go
this.
back, please, to the previous slides?
Yeah.
Oh, I cannot write on you. No, previous where you have a graph for Waxman-Solberman.
This one?
Okay. So you are using some kind of software that I cannot write on, so I will just be speaking. If
Okay.
you look at the loop at Vn, all right,
Yeah.
because this loop at Vn is the only edge emitted at Vn, it means that this partial isometry is in fact normal. It's a normal operator.
Yeah.
And in the case of the Waxman-Solberman presentation, you can look at the relation and you can realize that it is exactly the final generator that has the property of being normal, because all other generators are not normal.
Yeah.
And the upshot of being normal is that you can go one step further. You can declare the normal operator to be self-adjoint. And self-adjoint is a very special case of being normal. If you
Yeah.
declare a non-normal operator self-adjoint, you can kill too much of your algebra. So this is like in the classical sense. You say that one of your complex coordinates is in fact real, and then you have an even sphere. And if you look at this loop at the end, you can imagine that you take a pair of scissors and you cut this loop, and then you just have two. You have this place where you cut it, and the edge where it started. So at the vertex where it starts. And basically, what you do, this is precisely turning your normal guy into self-adjoint, and then you have to double the edges, because now these edges have to end at both of these vertices, in the old vertex, the end, and in the new vertex that you obtain by removing the loop.
Yeah.
So this is a way to think about how to see an even sphere inside an odd sphere, right?
Yeah. Yeah. So that extra loop here, that is just cut into these two.
Yeah.
These two additional vertices, something like that. So once we now have these definitions of real projective spaces, spheres, one more thing which we need is for the quantum CW complex or any CW complex is some notion of quantum balls. And in this case, we'll consider the quantum balls which are the Hong-Szymanski quantum balls, which are defined in the following way. So let T be the tuplets algebra, which is the universal C-star algebra generated by an isometry S. It also has a graph presentation, which is just like this. You have two edges and we have two vertices. So to define this quantum double suspension for any unital C-star algebra, this is defined as a C-star subalgebra of 8 tensor T, which is generated by A tensor P2, this vertex, A tensor S2, this edge, and one tensor P1 and one tensor S1. So this is strictly a subalgebra of A tensor T because we are not using all of the generators of T, but some of them. So this C-star algebra, this is the quantum double suspension. This is just a subalgebra of the tensor product. And because the tuplets algebra is nuclear, the choice of tensor product is does not matter. So classically, when we define, or not define, but classically, the higher dimensional balls and spheres, they are defined as double, or they can be thought of as double suspensions of balls which are two-dimensionless. So for instance, classically, when you take double suspensions, B2 for instance, the disk, it is a double suspension of B0, which is 2 points. So B2 is classically it's a double suspension. So we can emulate that quantum in a non-commutative way as well by taking quantum double suspension instead of just usual double suspension. So we define the higher dimensional balls BQn plus 2 to be the double suspension of C of BQn. And since we are jumping by 2, we need 2 initial starting points. So C of BQ0, C of BQ0 is just compact, not compact, sorry, just the complex numbers. So this corresponds to, again, just a single point, which is the classical 0 ball. So C of BQ0 is the same as classical 1. And C of BQ1 is also this classical, just the interval minus 1, 1. But because we are taking a quantum double suspension, C of BQ2, for instance, which is double suspension of this C, this is in fact the tuplets algebra or the quantum disk, and so on and so forth. So C of BQ3
I have a
again.
question.
Yeah.
Classically, double suspension can be realized as a smash product with a sphere, classical visual sphere. Can you see a sphere in this quantum double suspension?
So C of SQ n plus 2, for instance, this is also a quantum double suspension of 2-dimensionless. So
Okay, so this
yeah.
is what I expected.
Yeah.
But inside of this double suspension, so classically the double suspension is made with some geometric operation of the smash product with the usual sphere.
Yeah.
Pointed sphere. Is this sphere in this quantum picture classical? Is it a quantum sphere?
Let me try to answer it this way. Like in this bulk periodicity, you have the usual the usual double suspension is obtained by taking the tensor product with the sister algebra of all functions vanishing at infinity on R2.
So it is a sphere.
Exactly. And for quantum double suspension, this is just compact operators. And if you take 1 point compactification compact operators, you get Podlesh quantum spheres.
Podlesh. Yes. Well, okay. So this is what I expect.
Yes.
Okay, thank you.
Yeah, and this boundaries of these spheres, the quantum spheres, quantum balls, are in fact just the quantum spheres which we have discussed.
Exactly.
So C of
Yes, obvious
BQ3.
because you can delete the sink and all edges ending in the sink, and this is precisely your boundary sphere.
Yeah. Something like this. So we have a short exact sequence which maps BQ3 to S2Q, and the kernel is compact tensor. C minus 1, 1, for instance. This is just for odd one, but for even as well, we can have the boundaries to be which is just tuplets and compacts. So the boundaries of these balls are just the spheres which we have discussed earlier. And for even dimensional, they have just a normal directed graph presentation, which is just the same as SQ2n plus 1, but we don't have any more. We do not have a loop here. Instead, the final edge. So for BQ2n, it's exactly like SQ2n plus 1. So for 2n plus 1, we would have another Vn plus 1 and something like this. But we don't have this loop anymore. So the final loop becomes a sink. So we don't have this. The final vertex becomes a sink. And that's a graph presentation for even dimensional balls. So for even dimension, so now we want to have some pullbacks so that we are working with quantum CW complexes. So we want to look at pullbacks of C star algebras. So we want to show that C of RPQ2n, it can map to C of BQ2n, it maps to C of RPQ2n minus 1, and C of SQ2 n minus 1. This is in fact a pullback diagram. And again, this is inspired classically because even classically, when we consider the CW complex for a real projective space, it is in fact just RP1, for instance. This is just the CW structure is given by something like this. So RP2 is, we have just a single copy of, we just have a single 2 cell, we just have the boundary and constructs directly from RP1 to RP2. So so in the non-commutative case, we kind of expect the pullbacks to be of a similar form, of the same form. So we want to show that this is in fact a pullback, that C of RPQ2n goes to C of RPQ2n minus 1 goes to C of BQ2n, and this commutative diagram is a pullback. And for even dimensional ones, this is easy enough to see. So I'll just draw it for n equal to 1. But for higher ones, the same proof follows. So C of RPQ2n, this is like this, the graph presentation. Here we have, so for n equal to 1, we have RPQ2, we have C of RPQ1, this is C of PQ2, and C of SQ1. And C of RPQ1 is isomorphic to C of SQ1. Both are classical. Q does not matter. So both are just, the graph is just a single loop. So on the C star algebra level, I'll just note what is happening. So this particular edge, it goes to product of this edge twice on the C star algebra level, which is this. One of this edge, because we have two of them, one of the edge here, it goes to a loop of path of length 2. So it goes to this edge into the partial isometry corresponding to this edge. And the other one, that just goes to the other one directly. So, I mean, yeah, this is the map. And while this just embeds inside here, this loop just becomes this loop becomes this loop. And yeah, and this map, this is just taking this loop and mapping this twice. So exactly what is happening here, this happens for RPQ1 and SQ1 as well on this level. So we are mirror. So this is kind of the idea, like what is expected in a pullback, that whatever happens on this edge diagonal happens on this diagonal as well, and what happens this diagonal happens on this diagonal, the opposite things. So here this loop embeds here, this loop embeds here for these maps, but for these a edge of length 1 goes to a path of length 2. So here this one goes to this twice. And
so let me throw in a quick comment, if you don't mind. So this is precisely an example like this which motivated us to find a common denominator for both covariant and contravariant factoriality. Because if you look here, well, embeddings of the circles in bigger graphs, this is just taking admissible subgraphs. This is a very simple example of contravariant factoriality. Okay, so these are just graph homomorphisms. But if you look at the other maps, which are here completely natural, I mean, they are like the classical situation. And they really make this work in a beautiful and simple way. But you see, I'm mapping an edge to a path of length 2. So these are no longer graph homomorphism, and the induction is covariant, not contravariant. So this was very frustrating conceptually, because we had one diagram of graphs, but we applied two different factors. So that's why we came up with a common denominator, which is relation morphism. So now this is a diagram in the category of graphs and relation morphisms, and we apply just one contravariant factor to get pullbacks of C-star algebras. However, what is, it remains as a big open question. We would like to have, some properties defining when we have push out in the category of graphs and relation morphisms, so that with some additional spicing will give us pullbacks in sister algebras, and that's an open problem. Because we have it worked out for the contravariant deduction just for graph homomorphisms. But yes, we make sense out of what we mean by pushouts in a given category, and then we apply the functor, and then in order to get a pullback, we still need a bunch of conditions. But a lot of the conditions are already encoded by appropriate defining of what pushouts are in the category of graphs. And this is completely missing at the level of relation models.
Yeah. Yeah. Thank you for the comment. So, any questions in this for the until here? Okay.
I think that's good.
Okay. So for even until now we have only stuck with just usual directed graphs. Nothing is happening. We have not really used topological graphs. But for odd dimensional ones, this is where the topological graphs really come into picture. So the odd dimensional balls, they are not directed, just usual directed graph C-star algebras. There are certain obstructions to it that they cannot be the graph C-star algebra of a usual directed graph. But in fact, they are topological graph. There are no restrictions, and you can show that there is an isomorphism. So C of SQ3, for instance, if you remember, C of SQ3 was something like this, not like this, but so graph presentation for C of SQ3 is like this. You have just one edge, two vertices, one loop on each one of them, and one edge which joins them. So for the topological representation, we kind of replace this loop with a circle. So this diagram, we have this vertex, this loop is this loop, which is this vertex and this. But we replace this loop and this edge by a circle. So this loop becomes this whole circle, and this edge becomes this circle. So again, this is just a diagram. Here it looks like the edges don't have a topology. They look discrete, but in fact, they have the usual topology of a circle. This just is convenient way to draw them. Similarly, for C of B3Q, this can also be defined just like this. So we take an interval -1 to 1. We take a vertex V with a loop on it such that it maps one edge to each point on the vertex, which again have the same topology as -1 to 1. And the vertices will also have -1 to 1. And this is just the convenient way of drawing this. So for odd dimensional ones, they are no longer just directed ones. They have to be topological graphs in certain way. And C of RP3Q, which again also has a graph representation, which was like this. Instead of 1, we had 2. So just like C of SQ3, we just do the same thing here as well, that we replace this final loop by a circle and each of these edges by, so I don't know if it's visible, but here we have 2 edges. So from this vertex to each point, there are 2 edges, one corresponding to this circle, one corresponding to this circle. Of course, both of them start at this, but they end up also at the same. But this is, we replace this by a circle, this by a circle, and this loop by a circle. And this is in fact an isomorphism, which is explicitly given here, which here is the thing that an edge is going to, or the final loop or edge is going to a vertex projection. So using this.
So maybe this notation is a little bit misleading, because you are identifying, even in the previous case for even, you are identifying for CCQ. If one circle is a
Yeah.
topological space of vertices. But the other circle parameterizes endpoints of a family of arrows. So these arrows, they're like they form a cone, in fact.
Yeah. So this diagram, it looks like this is a
So
cone.
for me, it would be more natural topology of the situation. It's theoretically, it is equivalent. But I'm thinking about topology of this topological graph. I mean the topology of these arrows.
Yeah, so here they have the topology of
So this
S1,
looks,
but
yeah, so
just
this looks
to
like a
have
cone.
this looks like a cone, but just to draw them and have some pictorial representation, I just
Yeah.
use this.
But it's
Like,
only up to bijection. But
yeah,
it's
so
what's the topology of this space of arrows.
yeah, definitely. This is just like a way to
Okay.
draw them, just to visualize them. I mean, yeah, that's like one of the big advantages of directed graphs as well, that you can actually draw them. Right? And for topological graphs as well, up to a certain extent, you can also have such diagrammatic presentation with some loss of information, of course. So we want to look at this commutative diagram of C-star algebras, which is, again, I'm doing it for just n equal to 2, which is C of RP3Q case. But the same logic is true for all odd dimensional ones. So we have C of RPQ3. This is C of BQ3. And the boundary of the 3 sphere is again the 2 sphere, the equatorial polar sphere. And we have RP2Q. This way. So this map delta here, this is no longer a graph morphism. Here, at least in the odd dimension or the even dimensional case, it can be thought of, it was a morphism in some way that an edge is going to a path of length 2. But here, it's no longer the case. Because for odd dimensional one, even this map, which maps RP2Q to S2Q, this is not any sort of graph morphism. It is a map just on the level of C-star algebras themselves. So it kind of is expected that this map will not be either. So this delta map, this is essentially by if there's a function f on the circle, we map it to a function on the, so S1 is isomorphic to -1 over the identifying the endpoints. So we can have an embedding of C of S1 inside C of -1, 1, such that a function goes to a function here with f of -1 equal to f of 1. So a function on the circle can embed inside a function on the interval. And for the projections, for functions on this, that's exactly what happens. And same for the edges, that one of the T1 0 F0 that goes to T1 here, again, T0 and T1 are representations of the C-star correspondence. So again, it maps to a vertex and then some loop and some edge. And same, the last T1 0 F, it goes to the same here. And here the embedding is the same. So one of them, so because there are two of them here, one of the edges here, it goes to a loop and then an edge in some way. Not exactly, but in some way, this loop goes to this loop composed with this edge, like here. While the other one here, since there are two of them, the other one just goes to the edge here, this one. And these are again, of course, maps on the function. So the vertices do not embed inside the vertices or the edges, but the functions on the vertices embed inside them. But this is just a way of visualizing them. So here delta happens like this. And same thing with beta as well, the same kind of map. And this map, again, this can be thought of as we are taking an edge or taking a vertex here and splitting it apart into two. And here, kind of the same thing is happening, that we take a point edge here and we split it apart such that we get an interval. So it's not the same, but this is in fact a commutative diagram. And in some holistic way, it can be thought of as a vertex being split into two, while here a circle is being split into an interval. Like you're just cutting off this circle into this interval. Any questions? Okay. So here we use the admissible pairs, that the kernel of this gamma map, which is just embedding of this vertex into a point here. This is the gamma map. The kernel of this is in fact just compact tensor C0 minus 1, 1, which is exactly equal to the kernel of this map alpha, which is just compact tensor C0 minus 1, 1. Up a little bit. So this map, this is just compact tensor C0 minus 1, 1. Again, this is, we embed these 2 points inside the endpoints, and whatever is left, this middle part, which is just minus 1, 1, that the kernel just becomes compact tensor, whatever is left outside, which is compact tensor C0 on the open interval minus 1, 1. And the same thing here, because when we remove a vertex from a circle, that is homeomorphic to the open interval minus 1, 1. So, which is kind of the same thing which is happening here. So alpha mirrors what is happening in gamma, and beta mirrors what is happening in delta. And since they have the same kernels, and delta is an injective map which takes this kernel into here, this commutative diagram is in fact a pullback diagram. So we get so we have two kinds of pullbacks diagrams. We have RPQ2N, PQ2N minus 1. So we have two pullback diagram, and this further can be pushed down to PQ2N minus 1, 2, because of the other one. And so on and so forth. So we have any real projective space, then we have this particular sequence of C-star algebras which surjectively map from the higher dimension 1 to a lower dimension 1. So what we have in fact is just a filtration, that is 0, RPQ1, so on and so forth, RPQN for any n-dimensional quantum real projective
Let me make
space.
a quick comment about Pedersen conditions, because we call them like this because it's the best reference. There's a very beautiful paper of Pedersen where he studies in particular pullbacks of C-star algebras, and he just writes the necessary sufficient conditions for star homomorphisms to yield the pullback of C-star algebras when you have a commutative diagram. However, if you look into it, it has absolutely nothing to do with C-star algebras. I mean, these claims are already true for a billion groups. And I'm pretty certain, Tomek, so maybe you can help. Somebody must have proven it in some category theory book 50 years ago. But it's a bit unfair to call them Pedersen conditions just
Conditions.
because
Yeah.
we use a lemma proven in Pedersen's paper, but this lemma has absolutely nothing to do with sister algebras. It's purely categorical.
Yeah,
Yeah.
because it's based on the fact that the pullback in the category of sister algebras, it is a pullback of underlying abelian groups.
Yes, exactly.
Yeah.
Yes. But I'm wondering what would be a good reference. Who did it first? It's one of these folk knowledge theorems. You know. It's just an explanation that Pedersen. You say Pedersen conditions because we learned it from Pedersen's paper. But it's
Yeah.
by no means invented or discovered by.
Yeah, maybe it can be called as folklore conditions, maybe. Yeah. So that's the final result, that we do indeed have a CW complex for these quantum real projective spaces. Yeah. And with that, I would like to conclude my talk. Thank you so much.
Sorry, say it again. You finished,
No.
right?
Yeah.
Okay. Thank you so much.
Thank you.
I apologize for this confusion, but I remember that it has 40 slides, not 35. So
Those
I was,
are references.
Okay. Very good, very good. All right. So any questions, anybody? Tomek?
Yes, I would have two questions.
Yeah.
The first question is about orientability. It's a classical property which distinguishes between even and odd dimensional projective spaces.
Yes.
On the other hand, okay, so this was one question. So maybe I will ask another one, which is related. When we were speaking about this weak or K-weak gluing of this quantum CW complexes,
Yeah.
everything is based on complex K theory. But for real spaces, one can speak about real K theory. Okay, and then ask about this relation between orientability and properties of real K theory. So my question is there something similar in this quantum version?
I haven't really thought about real K theory. So odd dimensional ones are non-orientable, right? Not odd dimensional real projective spaces are not orientable.
So even that
Yeah, even are.
or not.
Yeah, so these complex projective spaces, they do have the same K theory as the classical one. So
Yeah, but it's a complex K theory.
theory, yeah. For
For
real
instance,
K theory, I haven't really thought about changing the field.
a
So
complex K theory, for instance, of a Möbius strip is trivial. Yeah.
yeah.
So complex K theory doesn't see orientability.
Yeah. Maybe if we have some sort of
So maybe some real K theory, which
Yeah.
makes sense here.
Yeah, it might be an idea because
Do people know the real K theory?
I'm not even aware if we have any non-commutative geometric definition of orientability or non-orientability. And maybe a good way to invent or discover such a definition is to
But
do
there are
real K theory.
also purely topological counterpart of orientability.
Like,
For instance, if you have a decomposition that you can speak about a sphere surrounding something, okay, then orientability can be reframed in terms of the Thom isomorphism. Okay.
okay.
So we have plenty of natural vector bundles over these projective spaces.
That is true.
So some questions about Tom isomorphism maybe could be good language for that. But I haven't seen
No,
paper
not have one.
with geometry.
This is a wild and undiscovered area here.
Yeah.
So I'm done with your questions. Or?
Yeah.
Okay. Łukasz? Anybody from the Zoom?
Yeah, so I have a question.
Go ahead.
So could you?
Can
I
you
don't
switch
have
on
a
the
camera.
because when you don't
I
see the
don't have
camera,
a. I do not have a camera. I'm sorry.
Ah.
I apologize.
Okay.
But can you go to the start of the presentation? So you started with the notion of a category with a name that has co-fibrations, right?
Yeah.
So I essentially wanted to ask you. So to me, this looks very similar to the notion called model categories. So is it for I don't know, maybe are those quantized CW complexes a model category?
Yes, they are. I think model categories are any category which has co-fibrations, right?
And fibrations. So
Model,
you need
fibrations.
But we also need
co-fibrations.
vibrations.
we
Yes.
don't have vibrations here.
Yeah.
But so
So
there's no
we
way to
cannot-
even define
So we
them.
cannot even ask about this lifting property.
But you can, for example, so in model categories, if I remember correctly, fibrations are supposed to be the set that you obtain. Well, you can look at some lifting problems and you can say what morphisms satisfy lifting problems for co-fibrations. And maybe you can declare that these are your fibrations. Or is it?
Yeah, there are dual classes with respect to the property of possessing.
Yeah, so I wonder. So I'm wondering. So because this is named unpointed Waldhausen category. Okay, so I was kind of confused. Why is it not like I don't know, like half of a model category or something? I was kind of I don't know, weirded out that it has a name. But so I suppose it's not a model category. Those quantum CW complexes. You cannot define fibrations in a nice way, I suppose. Or can you? Or is it maybe not? It might not have been considered. So that was my question, kind of.
So definitely there is a problem with the fiber, the notion of a fiber.
Yeah.
Here, it's an extension of the problem of non-existence of classical points.
Yes.
In non-commutative geometry. So.
Okay, so it might not be doable.
Even asking about fiber is sometimes nonsensical.
Okay.
Because usually bases have very few points, classical points.
Yeah, I mean, yeah, this is true. But you can do model categories on stuff without points. So I don't like chain complexes, stuff like that. So it's like
yes.
But okay, so if it's like kind of unexplored, then I was kind of just wondering.
Candidate for fibrations in this
True.
situation.
Yeah. Probably. Yeah. Okay. All right. So thanks.
Good. Anybody else? Adam?
I'm happy. Very nice talk.
Thank you.
Glad you liked it. Okay, there's nobody else. Let us thank ATUL again for a very beautiful talk. Thank you so much.
I think that there is a question from Ali.
Yes, I'm sorry for my delay. Can I ask a question?
Yes. So why didn't you ask that earlier when I asked if there's any question?
Yes, thank you very much for your very interesting talk. My question is somehow inspired by the question of is in line of the question of Tomac. He was inspired by the classical case and orientability, but according to the classical case, the embedding of the RPN in RPN plus 1 gives give an isomorphism in the singular cohomology between two space. It is a classical fact in algebraic topology that the embedding of RPN in Rpn+1 gives an isomorphism in a singular cohomology up to dimension n. So is there a possible quantum analogy of these facts, for example, in terms of Hochschild cohomology, which is a non-commutative candidate for the Durham cohomology? So I mean that let we have a surjection from the quantum sphere of dimension n+1 to the quantum sphere of dimension n. So are there some results which, for example, says that this gives an isomorphism between certain cohomologies, say Hochschild cohomology or something else? Do you think that this is a good question for doing for research or no?
Yeah, that's certainly possible. Like maybe there is some isomorphism on the cyclic cohomology or Hochschild cohomology, but it's not something that I've really thought about before. But yeah, it's certainly a possible and a very interesting question.
Yes.
So, may I have a comment to this question?
Yes, yes.
So if you have this machinery of these CW complexes, or quantum CW complexes, you have plenty of fixed exact sequences.
Yes.
And then you can have something, at least in the complex case, for instance, on the level of K theory, you have such similarity to the classical picture. The problem is that the complex K theory for real spaces is not as developed. Okay, you cannot do the same what is possible for cohomology. You need some real K theory sometimes. So there's a problem. So this nice picture from complex projective spaces, when you have this tower of these truncated polynomials in a single variable, doesn't work here. But it doesn't work even classical, because complex K theory is not good for these real projective spaces. So all the difficulties are related. So orientability, applicability of this nice algebra from the complex case to this real case on the level of K theory, all these problems are related.
Yes, I see.
Okay.
But in the context of cohomology, it doesn't depend. The fact is, doesn't depend on the K theory. But
then it would need cohomology, for a singular cohomology with coefficients in two-element field to be sure that everything behaves well. And such cohomology has no analog in non-commutative geometry. So periodic cyclic homology is not a good extension.
Yes.
Ali, are you happy? Can we wind it up?
Yes, thank you.
Thank you again.